Hello, we want to inspect the diesel engine fuel tank together and design it in GT Power software. So the main thing is to supply the engine with clean, water-free fuel. As you can see in this picture, we have fuel tank. This is where the fuel is stored. It will have a filling pipe, normally from deck. It also has a vent. This is very important as the tank is not a pressure vessel. As the tank is emptied or filled, air has to be allowed in and out. So, ideal tanks also have a drain on the bottom to drain water and sediment after it has settled. The engine designed in GT Suite or GT Power consists of the following components: fuel tank, low pressure feed pump, high pressure fuel pump, fuel rail, injectors, injector, and pressure regulator, turbocharger, intercooler, intake and exhaust manifolds, air intake system, cylinder, crankcase, intake or exhaust valves, and others. Let's go to fuel tank design. To design the diesel fuel supply system, fuel tank must be modeled in GT Suite to allow for the integration of the fuel bypass circuit back to the tank. Okay, you can see this picture here in GT Power actually, and this picture illustrates the fuel tank system designed in GT Suite to facilitate a better understanding of the system. Numbers have been used as follows. Number 1 represents the accumulator fuel tank, and number 2 the outlet from the tank towards the low pressure pump or feed pump, and number 3 the fuel return line from the low pressure regulator. Number 4, the fuel return line from the high pressure regulator. And number 5 is the fuel inlet pass back into the tank. Let's go to the accumulator. Okay. This object is used to model an accumulator that has constant volume of two fluids that are separated by a massless membrane. The total volume in the accumulator is always conserved, but the distribution of volume between the two parts freely changes as necessary to maintain a balance of pressure. Okay, let's go through main tab. Total volume. Total volume of the complete accumulator assembly. This includes the volume of both fluid sides that will be modeled. Okay. Fluid 1, initial volume. The initial volume for fluid 1. The difference with the total volume will be used to initialize the volume for fluid 2. And fluid 1 initial volume fraction, a fraction of the total volume. The difference with the total volume will be used to initialize the volume for fluid 2. And geometry. User can select between the simplified geometry option of the custom geometry option below. The simplified approach assumes a square cylinder geometry. Diameter is equal to height, which the custom option requires geometry input from the user as a function of the fluid one volume. Default geometry assumes a square cylinder. Total fluid to wall heat transfer area. The user defined total heat transfer area between the fluids and wall of accumulator. Fluid 1, wall heat transfer area object. The name of an XY function or XY table. Reference object to define the wall heat transfer area of fluid 1, Y, as a function of the fluid 1 volume, X. The wall heat transfer area for fluid 1 cannot exceed the total wall heat transfer area defined above. So the wall heat transfer area for fluid 2 will be calculated as the difference between the total wall heat transfer area and the wall heat transfer area for fluid 1. About fluid 1-2 interface area, the area of constant between fluid 1 and fluid 2 used for heat transfer calculations. An object can also be entered to describe this fluid area contact, where X is the volume of fluid 1 and Y is the fluid heat transfer area when using an XY function or XY table reference object. And what about fluid 1 initial state name? Name of the fluid initial state reference object describing the initial conditions inside the accumulator for fluid 1. And fluid 2 initial state name of the fluid initial state reference object describing the initial conditions inside the accumulator for fluid 2. So let's go thermal behavior. Impose wall temperature, specify the wall temperature or the name of dependency reference object. Model wall with integrated thermal mass. If this option is selected, wall of the accumulator will be modeled with thermal primitive as an internal compound similar to the layout in the picture. This. And we have internal thermal node reference object, external convection temperature, the value of the ambient temperature or the name of the dependency reference object, an external convection coefficient, the value of the convection coefficient between the wall and ambient temperature or the name of dependency reference object. And model wall with connected external thermal primitive. If this option is selected, the heat transfer rate from the fluid to the wall will be modeled through the use of thermal primitives that connect to the accumulator part. Thermal primitive will need to be created by the user. And what about options? The first one, the value of the convection coefficient between fluid 1 and the wall. And fluid 2 wall convection coefficient, the value of the convection coefficient between fluid 2 and the wall. And fluid 1 wall heat transfer multiplier, value of the heat transfer rate multiplier between fluid 1 and the wall. And the other one, value of the heat transfer rate multiplier between fluid 1 and the wall. Heat transfer coefficient between fluid 1 and fluid 2. The heat transfer coefficient between fluid 1 and fluid 2 for heat transfer calculation.